Hello, welcome back. No handouts today for a change. You should all be working on homeworks and programming assignments. The second homework is due Thursday. The programming assignment is due next Tuesday, a week from today. I assume everything is going okay. Is there any questions or problems? Now's a good time to raise them or talk to me or the TAs. Yeah.
I have a problem with the programming assignment. When I logged into the Adelbert, because I have an account that's supposed to be on Leland, which I guess is just Elaine. When I logged into Adelbert, it said that the file systems, the NFS file systems, are no longer mounted on the Adelbert, and I can't access my account and do anything on the Adelbert.
Oh, that's not very convenient. You know what's going on there, David?
Yeah, that's not very convenient at all. The computing center is trying to switch everybody over to AFS, and since they won't sort of force you to go to AFS, they start doing things like getting rid of NFS accounts from Adelbert. So in order to actually compile the stuff, you either have to have your partner on an AFS account so you can get to Adelbert, do some strange FTP stuff, or just switch to AFS.
If you didn't understand that, talk to David. He's the expert and can get you up and running.
If you convert to AFS, will it still work on the Elaines? Or okay.
Okay, last time we had begun our survey of real computer architectures, instruction set architectures, and today we're going to continue with the Intel x86 series and the RISC series, a typical RISC, but we'll talk about some specific ones as well. The Intel x86 architecture is an architecture that gets no respect. In fact, even the book makes a bunch of snide remarks about it, saying something like it's an architecture only its mother could love, or something like that. And in part, that kind of derision is fair, but in part it's not fair, because if you look at the current instantiation of that architecture, the 386 and beyond, it's not all that bad. But it has to carry an awful lot of baggage from ancient history, and part of that baggage is what makes it look bad to people. And also sometimes people remember and focus on the old stuff rather than looking at the subset of the current architecture that actually looks like a reasonable computer. And we'll see that at the heart of an Intel 386, there's a semi-reasonable instruction set architecture struggling to get out, but it's encrusted with all of this ancient history. Let's look at where that ancient history came from. It started back in 1970. In fact, Intel was the first manufacturer, they would claim, and I believe, of microprocessors. The first one they built was actually a 4-bit microprocessor for calculators, but the first real general-purpose machine was in 1972. It was the 8008. And in fact, they had designed that jointly with Datapoint of Texas as a chip to be used inside a computer terminal, a terminal for a mainframe. As it turns out, Datapoint co-designed the instruction set with Intel for that processor, but never used it in a terminal because Intel was too late in producing chips that Datapoint could actually build something out of. So in fact, Intel then decided to sell it as a general-purpose computer, which they did. 2 years later, they realized that the kind of very limited functionality of the 8008, like, for example, 14-bit addressing and an on-chip stack for subroutine calls that was only 7 beats, so you could never call subroutines any deeper than 7 levels, was rather confining, and they extended and redid the architecture and turned it into the 8080, which was a more general-purpose computer with 16-bit addressing, could directly address 64K, and was reasonably clean. Which reminds me, I brought this week's historical artifact, which is in fact the first commercial board built using an 8008 processor. The interesting thing about the 8008 in a board like this is, in fact, it's hard to figure out where the processor is. Usually these days you look for the biggest chip with the most pins and probably a heatsink. But in these days that wasn't the case. And in fact, the processor is this chip over here. It's just an 18-pin IC with multiplexed address and data buses. And all of the rest of it is support circuitry. And this ran at, I think, 1 megahertz clock or something like that. These are RAM chips. Those are 256 bits each of static RAM. So the total RAM memory on this board is 1K bytes. Well, the machine could only address 64K, so 1K was a reasonable leg up on that, at least. These were read-only memories that are programmable. You could erase them by putting them under an ultraviolet light or a desk lamp sometimes. and programmed them with a special machine, and these contained, I believe it was 1 KB each, or 512 bytes each, something like that. In any case, very, very limited storage capacity. But leave this up here for anybody who wants to look at it. Something from that same vintage, by the way. Floppy disks came out at about that time. And, oh, here it is. And just in case you've never seen it, the floppy disks of that era looked like this. They weren't the kind of thing that you put in your shirt pocket. These were 8-inch floppy disks, and this stored about 128K or 256K, something like that. They began to shrink after that. Anyway, the progression from Intel was that they realized that the 8080 was limited primarily because of its 16-bit addressing and the limitations to 64K. So the first step, in fact, was to extend it in the 8086 in a way we'll see in a second to allow more addressing. And in fact, it's called segmentation, but really is a pseudo-segmentation that allowed them to extend up to 20 bits of address rather than 16 bits. They added some more registers, added some more instructions. And in fact, I believe this is true, somebody correct me if I'm wrong, that the transition between the 8080 and the 8086 was not binary compatible, but it was machine level compatible. So that if you took your assembly language program and reassembled it, producing a new binary, it would run. You didn't have to change any of the instructions. But the actual opcode encoding wasn't the same from the 8080 to the 8086. Can somebody confirm that? No. Okay. The next step was actually not an architectural change, but rather an implementation change. A year or so later, they came out with the 8088, which had exactly the same instruction set architectures, 100% compatible in binary format with the 8086. And the difference is it had an external 8-bit bus rather than an external 16-bit bus. And this was the machine that, in fact, IBM adopted for their IBM PC, first IBM PC at the time, and the rest is history. There is some speculation, I speculate at least, that if Motorola had come out at about the same time frame with the 8-bit version of the 68000 series architecture, the 68008, IBM might well have chosen the 68000 instruction set architecture to base their PCs on, and we wouldn't today be talking about x86 architectures at all, because they probably would have disappeared. But they didn't, and IBM did, and now, as I pointed out last time, a majority of the 150 million computers on this planet are using this architecture. In 1980, they added floating point, but they couldn't fit it on the chip because the integration level wasn't sufficient at the time, so they added a separate floating point coprocessor, which has eventually been integrated into the same processor, of course. There were some other minor versions on the way, like the 8186, which was used primarily for people building embedded systems because it integrated onto the chip some of the peripheral controls that used to be in separate chips, in particular the DMA, the direct memory access I/O channel for doing I/O operations. But the next major change was in 1982 when they announced the 286. And this is the point at which they really have true segmentation. We'll see how that works. They went from 20 to 24-bit addressing. They invented an elaborate protection model that allows multiple rings of protection from user state to kernel state and complex transitions from one to the other. But they realized that that mode, which was incompatible with the original 8086 mode, couldn't be used for existing software, like, for example, DOS, the disk operating system. So, in fact, they had a real mode subset, and once in that subset, you could execute exactly the binary programs that you could have before in 8086 mode. Unfortunately, switching from one mode to the other required almost a power-on reset of the machine, which made operating systems that transparently ran tasks in 8086 mode at the same time they ran new tasks in the new mode very difficult to implement. Well, they fixed a lot of those problems in the next generation, which was the 386. In that transition, they went from 24 bits to 32 bits. They added, in addition to the segmentation that they had introduced in the 286, they added on top of that, as a second stage address calculation, a paging scheme, sort of traditional fixed size 4K byte paging system. In each of these transitions, they've been adding somewhat new instructions to do interesting things. They now have changed the 8086 emulation mode just a bit and called it a virtual 8086 mode. And it's done in such a way that the transition between old-style 8086 mode and new-style, either 286 or 386 mode, can be done on a task-by-task basis. So, in fact, you could write an operating system, and they did, which allowed individual tasks to run the old code in 8086 mode and new tasks to use one of these new schemes, either the 286-like scheme or the 386-like scheme. From then on, the changes are not primarily architectural. They're mostly implementation. The 486 adds only very few features as far as the instruction set architecture is concerned, and is mostly a performance enhancement, and that tradition has been carried on. They realized the trauma that it causes to make these radical changes that they did prior in the history, and they continue to increase in performance without affecting the programmer visible architecture. And the next step here is the P6, which is going to come out sometime in '95. I think next month they're about to announce officially this part and describe the details of it and give people expectations about what its performance might be. Questions? Okay, so what does it look like inside? Mostly I'm going to be focusing on the 386 because the rest of it is ancient history, although some people devote their lives worrying about that ancient history. But from a 386 point of view, it's basically an 8-register, 32-bit wide register machine. Because of that history, some parts of the 32-bit registers are in fact given special names and can be accessed separately by the instructions. So these were the registers that existed in the 8086. The low-order 16 bits of them are all addressable as separate named registers, AX, BX, CX, and DX. Those, in turn, are also subdivided into 2 8-bit registers, and there are separate instructions, for example, that can move AL to CH, which is not something in a 32-bit machine that you would necessarily do, but is still there for compatibility with the older modes. So there are 8 32-bit registers. Many of them have special functions, as we'll see. One of them is the stack pointer, which is used for pushes, pops, calls, returns, and all of those functions. There's a program counter, which is 32 bits wide. There is a processor status, which contains condition codes and other information, which is also 32 bits wide. Now, in addition to those registers, there are also segment registers, which are used differently in the 8086 style instructions, in the 286 style instructions, and the 386 style instructions, and we'll see how that is. But basically, these are internal registers which are visible to the programmer that are used in the computation of effective addresses. If you want to compute what memory location to reference with the program counter, you have to use not only the contents of the program counter, but also the contents of the code segment register, which contains some information that helps you determine what the ultimate memory location is. There's one of those for code references, there's one of those for stack references, that's the SS. There's one of them for implicit data references, which is DS. And then there are 3 others that are sort of general purpose segment registers that can be used at programmers' request for referencing data. Some of them are in fact used implicitly, as we'll see, but most of them are available for use by the programmer for making data references. Now, part of the problem, and one of the reasons why this kind of a machine is not as attractive to programmers compared to a RISC machine, is that most of the registers are not truly general purpose. For example, when you're doing multiply and divide instructions, implicitly EAX, the extended AX register, and EBX are used as some of the operands for the multiply and divide instructions. Similarly, when you're using certain stack segment references, it implicitly uses EBP. It also, in fact, when you explicitly use EBP, uses the stack segment register instead of one of the data segment registers. So there's not only dedicated or implicit uses for registers, but also dedicated or implicit uses for the segment selectors as well. When you do string operations, like copying a string from one place to another in memory, the SI and DI, source and destination index registers, that's what the name comes for, are used implicitly. There's no way to override that. If you've got something else in those registers, you've got to save it and restore it in order to be able to do a string operation. The CX register, the extended CX register, is used for loop counts. There are loop instructions that decrement the CX and continue looping until it gets to be 0. Still, even with all of these registers which are assigned special purposes, the architecture at the 386 level is much better than it was in the versions before that. Okay, what do operands look like? Well, register operands are obviously available for almost any operation, and those registers can be 8-bit registers, 16-bit registers, or 32-bit registers. So it can be an AL type reference, it can be an AX type reference, or an EAX type reference for 8, 16, or 32 bits. There are immediate operands available for 8, 16, and 32 bits. There is one kind of general purpose memory access mode, which is a form that we've described as scaled mode, where you take a base register, and this, again, depending on what mode you're in, could be 16 or 32 bits, plus a second register which is scaled by a constant, either 1, 2, 4, or 8, and then you add to that an offset from an immediate field, which could be either 8 or 32 bits. So this is the kind of general purpose addressing mode. But in fact, there are subsets available for several of the reasonable kinds which are implemented with shorter encoding than this general form. So there's an indirect register format. There's a indirect register format plus displacement. There's a form that simply adds 2 registers with no displacement. And then there's the register plus displacement form, again, without scaling, or where the scale factor is 1. So in some ways, the memory effective address generation is fairly general, and it's fairly orthogonal, that in almost all cases where it would ever make sense, you can use any register for these register designators. You can use EAX or ESI or EDX without being concerned about whether it's legal or not. That wasn't true in the versions before the 386. And because all of these machines are binary compatible, it means that the encoding for these various addressing modes is rather bizarre. The encoding for register modes that correspond to things that existed in the old machines, like 286s, are smaller typically and take less bits. But if you make an innocent change, like you change ESI to EAX, you just change the name of which register you're using in one of these addressing modes, then in fact the entire form of the instruction may change, because now it's no longer a 8086 or 286-like instruction, it's a 386-like instruction. Mostly the programmer and the compiler can ignore that unless it's interested in the absolute minimum encoding of any particular instruction. So a lot of that complication is hidden from everyone except the compiler writer or the assembler. Let's take a look at the memory architecture, and here we'll talk not only about the 386 currently, but about the progression and how it moved from the old style to the new style in a way that they attempted to make backward compatible. Remember, the 8080 was simple. It had a 16-bit address and addressed 64K of memory, and there was no complication whatsoever. In order to extend the 8086 to 20 bits, what they did was to invent segment registers. At least they called them segment registers. What they really are is an extra register which contains 16 bits of address. And within the instruction, some offset is specified, and they produce the effective address by adding together the segment register, shifted left by 4 bits, so there are 4 zeros here, and produce ultimately a 20-bit address. This is the 8086 mode. Now, people who know and love segmentation would claim that this is not segmentation at all, or at least if it is, it's a very primitive kind of segmentation. This turns out to be very difficult to manage from a programming point of view because, for example, all segments are limited to 64K. So in fact, anytime you want to reference a data structure that goes beyond that, you have to manipulate not only the offset part of the instruction, but also the contents of the segment register. And the segment registers are loaded and stored by separate instructions. So the process of addressing a particular place in memory involves two operations. One is changing the contents of the segment register, and the other is adjusting the offset. Notice, because the segment register is shifted left 4 bits, that segment boundaries are on 16-byte boundaries. So you can't even use the segment register to point to an arbitrary place in memory. You can only point to the nearest 16-byte boundary and then use the low-order bits of the offset to address the rest of it. Okay, so what did they do then in the 286 to make life better than that? Well, they introduced what really is real segmentation. In the 286, you now still have segment registers, but rather than containing a number which is directly added into part of the memory address calculation, the segment register contains 13 bits, and those 13 bits are used to look up information in a segment table about that segment. And one of the pieces of information in that segment table is the base address of that segment. And the base address now is, let me make sure I get this right. The base address now is a 24-bit quantity. You add to that 24-bit quantity a 16-bit offset from the instruction, and compute a 24-bit effective address. Well, what are the advantages here? Well, for one thing, we've gone from 20 bits to 24 bits, which helps a lot. For another thing, the addition of the offset within the instruction or within program registers is done without any shifts. So in fact, segments can begin on arbitrary boundaries. The problem is that segments are still limited to 64K because the offset is only 16 bits. So you can't ignore segment registers. You still, in referencing large objects or in referencing objects whose aggregate is bigger than a single segment, have to manipulate either the segment registers themselves or the contents of the segment table. Segment table is typically set up by the operating system and is a protected structure. Segment registers are available to user state programs. So you would have to negotiate with the operating system to get all of the segment registers pointing to appropriate elements in the segment table to reference your data. Still relatively complicated, but in fact has extended the addressing at least to 24 bits. One of the other changes they made as part of this extension to the 286, in addition to address segmentation, was the addition of lots of other complication for tasking and interrupts. And in fact, there are 15 types of segments, only some of which are memory blocks. Some of those segment types represent calls, they represent procedures, they represent traps or interrupts. And in fact, there's a very complicated mechanism for doing a call or a return referencing a segment to indicate where that call or return should go. They added multiple privilege levels, so now that there are 4 levels of privileged operation between user state and kernel state, and lots of rules that describe how it is you make a transition from one privileged state to another, all mediated by this segment table, which has bits that control the segment types and the privilege levels and so forth. One of the problems is that an instruction as innocent as the call instruction becomes extremely complicated. The description in the 286 book of how the call instruction works is detailed in a flowchart that goes on for about 4 pages of number 10 type. It's difficult to understand, and it's difficult to implement, obviously, if you're an architect or implementer of that instruction set. In the 386, they did a couple of different things. One is, as I mentioned, they added onto the segmentation a paging scheme that uses fixed 4K byte pages. And this is a second operation. After going through the calculation of the effective address that I just showed you, they treat that effective address as a virtual address, translate it to a real address using a fairly conventional paging scheme. And we'll talk more about that in the second half of this class, but I'm sure you've seen some of that before. But the other change they made in the segmentation part in the 386 was that the segment register, which is as it was before, still a 16-bit register of which 13 bits identify a descriptor in a segment table. These are the segment descriptors. One of the fields in the segment descriptor now is a 32-bit value instead of a 24-bit value, which is the base address. But they also allow offsets within the instruction to be either 16 bits or 32 bits, producing a 32-bit address. So the effect of this now is that, number one, not only did they allow 2 to the 32 bytes to be addressed, or at least virtual bytes to be addressed in the machine, but they allowed segment numbers to be as large as 2 to the 32. Whether or not offsets for a particular segment are 16 bits or 32 bits depends on type information that's encoded within the segment descriptor. But what this means is that, in fact, if you choose to, you can ignore segmentation on the 386. You can choose to have all of your segment registers have descriptors which point to a flat linear address space of 32 bits. So it's possible in this mode to have a linear 32-bit address space, much like a simple RISC processor. In fact, this is a subset of the 386. It's a subset that gets used more and more often. Operating systems like NT for Microsoft basically ignore segmentation, except for some edge cases, and treat the 386 or the 486 or the Pentium as if it were a non-segmented 32-bit addressing machine. In fact, even in operating systems like Windows 3.1, there is at the base of it a nice little 32-bit virtual kernel which operates entirely in 32-bit flat address mode. But unfortunately, for compatibility with older software, a lot of the rest of the operating system has to expose the segmentation of the 286 and prior machines. Questions or comments?
I have a question as far as the Pentium. I guess this may get into something in the future, but how do they do a superscalar implementation when there is multiple or different length instructions?
It's very difficult, and in fact, I'll talk about that somewhat, probably in a week or a week and a half. One of the disadvantages of doing high-performance implementations in general of 386 or VAX-like machines is the decoding problem, because you can't tell by looking at the beginning of an instruction how long it is or what operand it's going to reference. The answer is it's very difficult. More later. Yeah.
Is it effective there?
Well, it can be. In fact, one of the techniques for making high-performance implementations of things like the Pentium, and NextGen is doing things like this, is in fact on the fly to translate 386 ISA instructions into RISC-like instructions. And then you feed that RISC-like instruction stream to a conventional pipelined high-performance implementation, like a superscalar implementation. And that's one way of getting around the fact that it's very difficult to directly get high-performance implementations of this architecture. They do an on-the-fly translation. Good question. Okay, what are the 386 instruction types like? Well, they're fairly conventional. They have the standard kind of data movements, moves, push pops, and conversions from different lengths and from fixed and floating points. The ALU operations are unsurprising. They do have an add and subtract with carry and borrow to enable you to do multiple precision arithmetic. So add with carry, in addition to producing a carry, also uses a previously set carry so that you can iteratively produce multiple precision results. They don't have decimal arithmetic per se, but they have some instructions that assist in doing decimal arithmetic. They have correction instructions that allow you to use the binary adds and subtracts, and then they correct for the internal carries so that you can do BCD operations. And the usual logical operations, shifts, rotates, and tests, and so forth. In some ways, they were relatively restrained. It's not a VAX-like instruction set, in part because of its history. They couldn't possibly have implemented a VAX-like instruction set on a microprocessor, and this was the first instruction set that was exclusively designed to be implemented on a single IC. By the time there got to be enough transistors so that one could consider implementing a VAX-like instruction set on a single IC, it wasn't politically correct to do it anymore, and they recognized that the RISC-like instruction set was by far a better approach to get high-performance machines. So the result is that the 386 instruction set, in terms of the basic instruction types, is not as bizarre as the VAX. Control flow, in some ways, is like the VAX. It's a traditional condition code machine. Most instructions, well, I wouldn't say most, but a majority, I guess that's the same as most, but many instructions set the condition code, not as many as the VAX. For example, on the 8086, as I mentioned last time, increment and decrement don't set condition code, so that you can use increment and decrement to get the effect of auto-increment and auto-decrement addressing without destroying a carry that might be used for an add with carry or subtract and so forth. Conditional branches within the same segment allow 816 and for the 386 32-bit offsets. Because of the segmentation, jumps and calls have to be allowed to not only change the offset of the instruction pointer, but also have to be able to change the segment number. So in fact, there are different kinds of jumps and calls for intra and intersegment jumps. Intra-segment meaning within the same segment, and intersegment meaning to a different segment where you have to change the segment number. In addition, for addressing of data which is not in 32-bit flat mode, you have to decide whether a reference to data contains a segment reference or not. And in fact, that leads to two different kinds of pointers. Can I describe this anywhere later? No, probably not. Pointers on this architecture can be of two types. They can be far pointers or near pointers. Near pointers are just the offset part, which means it's within the current segment, and far pointers are the segment plus the offset part. Not plus in the addition sense, but plus in the sense that both of these components are used to describe a pointer to data. And in fact, in non-32-bit uses of this architecture, these different kinds of pointers are exposed way up to the programming level. And in fact, the C language compilers for this architecture has facilities added to it for you to be able to declare pointers to be far or pointers to be near. Now, in the 386, remember, offsets can be either 32-bit mode or 16-bit. If you choose 32-bit offsets, then you can always choose to use near large offset pointers, and that's the mode in which it becomes a 32-bit flat addressing model, and you can ignore segment registers. That's the mode which most new software tends to use for the 386. There's a small diversion away from control flow into pointers in general, but that same distinction between far and near pointers applies to jumps and calls for doing intra and intersegment references. There's a simple loop count instruction that decrements CX and might also, in fact, test a condition, one of the condition codes, and branch back. There are a couple of enter and leave instructions for procedure entry and exit that do some amount of stack frame maintenance, not nearly as complex as the VAX, and in fact, it tends to get used by the C compiler because it's simpler and somewhat easier to target as an output of the compiler. String instructions, as I mentioned, use special registers, the DI and the SI registers, for pointing to the source and destination operand, and effectively get auto-increment and auto-decrement mode without it having been part of the general addressing mode. So if you do a string move instruction, for example, it references the byte at ESI, stores it in the location that EDI is pointing to, and then increments both ESI and EDI. Now, in fact, that instruction doesn't do any more than a single byte, and you'll see later how you can either put that instruction into a loop using the loop count instruction, or you can prefix that instruction with a special modifier that says execute that instruction over and over again until the loop count goes to 0. Those string instructions are used for moves, compares, scans, loads and stores, and so forth. And I just mentioned this, that in fact those string instructions do only one cycle of that operation, and there's a prefix byte that you put in front that says re-execute that instruction over and over again. Basically, set the program counter back to point to the instruction again until the loop count has gone to 0.
Question?
Yeah.
When you say until the loop counter goes to 0, you mean the same loop counter as we use for the loop instructions, that is CX? Or
yeah, absolutely. The same loop counter, it is CX. And if you're using that as a prefix to an instruction, you can't embed that in another loop that uses CX unless you save and restore CX. There's only one loop count register. This is the ugly part of the 386 based on its heritage, because it had to be binary compatible going back to the 8086. Instructions are 1 to 15 bytes, and in a kind of unusual quirk of fate, they don't even start with the opcode. They may, in fact, start with a whole collection of prefix bytes, which have to be fetched, interpreted, and remembered by the processor before it even gets to the opcode to know what kind of instruction it is. Well, one of them we've just talked about. It's this repeat prefix that basically says whatever the following instruction is, keep executing it until CX becomes 0. And that gives you a way to take string instructions and that operate on a single byte and make them the multi-byte instructions. Remember that I said that in the 386, segment offsets can either be 16 bits or 32 bits, depending on what the segment descriptor says about it. Well, sometimes that's not convenient. Sometimes you want to, in a 32-bit segment, encode a 16-bit operand or a 16-bit address offset. Well, they allow you to do that, and the way they allow you to do that is to have two different prefixes. One is the operand size prefix, which is just a constant byte, and the other is an address size prefix, which is a different constant byte. And if you put either or both of those in front of an instruction, it says reverse the decision that the segment descriptor implies about whether offsets or operands should be 16 or 32 bits. So you can, on an instruction by instruction basis, change what the offset is. Segment override is a way to change what the default segment register used is. Remember I said that certain stack references, for example, use SS segment by default instead of DS, which is the data segment. Well, you can change that. You can say that the following instruction should use DS or ES or GS instead of the implied default segment. And that's very handy in non-32-bit mode, where you have to be, as a programmer or as a compiler, manipulating segment registers in order to be able to access things bigger than 64K. You have to manage segment registers and their contents, as well as managing the registers containing the offsets. And being able to override the segments is a handy thing to do. Bus lock is a facility for making multiprocessors. It basically says that during the execution of the following instruction, you should prevent any other processor from accessing memory. And that's a way to get atomic operations like increment to fetch, manipulate, and store back a memory word without the opportunity of some other processor getting in there and reading an intermediate result. So all of those prefixes first, then the opcode, and sometimes the opcode takes a second byte as an opcode extension. Then 1 or 2 bytes of address information that contain the register numbers being referenced, that contain information about if it's scaled mode, what number to multiply by, and what the second index or base register is. So there are 1 or 2 bytes of encoded register and address modification information. And then either a displacement or immediate field, which is 8 to 32 bits, implied by some combination of the addressing modes, the opcodes, and the operand. Yeah.
For the bus lock mode, how do you prevent, say, if it's multiprocessor, how do you prevent other processors from accessing memory if you just lock this processor?
Well, what the bus lock does is create an external signal coming out of the chip that says, I'm doing a bus lock operation. And it's the responsibility of the memory designer to make sure that the memory looks busy to all other processors while that operation is in effect. So really all bus lock does from the processor point of view is create an external signal saying, please give me exclusive control to the memory until I say otherwise. Okay?
Why would something like the operand size and address size have to be a prefix?
I'm sorry, I can't hear you.
Why would the operand size and address size have to be a prefix to the opcode?
It wouldn't have to, and in fact, I guess you could redesign it so that that information was encoded in the addressing mode over here. It has to do with the historical backward compatibility. This mode RM byte existed back in the 8086 mode, and there was no extra way to, there was no other way to encode that information. The other thing is the guess that these things would be rarely used, and you wanted them, in fact, to be optional and not to take up fixed space in the standard address encoding. Yeah.
My question was about those prefixes there's not always room for them in every instruction. There aren't so many bytes or bits out front.
No.
So how can you tell if you're looking at a prefix or not?
Because it turns out that all of the prefixes, and I guess there are 1, 2, 3, 4, 5 of them, happen to be different than the opcode. They don't duplicate the value of any existing opcode byte.
Essentially, we're looking at a lot of different flavors of opcode.
Yes, you could say that. I mean, you could, in fact, describe this, the combination of prefix and opcode as the opcode. Right? But then you wind up with, let's say there are n of these opcodes, and there are 1, 2, 3, 4, 5 of these prefixes, you wind up with n times 2 to the 5th different opcodes. It's a harder way to describe what's going on. But you're right. It's equivalent. Okay, that is all I want to say about the 8086. And I suspect there are probably some of you out there who know a lot more about it than I do. And it's an architecture that you can spend your life enjoying and programming. David?
Hello.
Yes.
So I have a question.
Yes.
Since we are talking about bus locks, I'm going to ask you something about MP issues with the 386.
Okay.
When the 386 sets a reference and modified bits in hardware, what happens if two processors are going to set the same bits on the same page table entry?
Two processors, generally speaking, don't share the same page tables or segment tables. They share memory, but they have private versions of segment tables and page tables for themselves. Does that answer the question?
What about shared process groups like threads running, which have like one thread can be running on one processor and a thread from the same process group could be running on another processor?
Yes.
And they both happen to access the same page table entry at the same time. So don't they have to update the same memory location?
They could certainly have access to the same memory location. I think most operating systems that implement something like that use separate, at least segment tables for the two different processors. They may, in fact, describe the same area in memory. So going through their independent segment tables, they could be accessing the same memory location and therefore share segments or individual pieces of memory. In which case, when they're making atomic operations to update memory, they need to assert the lock operation to keep the other processor from accessing it.
So this is all done in hardware when like the reference and modified bits are going to be set? Because those are set by hardware, right?
I don't quite understand. We're going to be addressing more multiprocessor issues later. Maybe you'd better separately give me a call and we can talk about this. I don't want to take a lot of time now for multiprocessor issues.
Okay, thanks a lot.
Sure. Okay, now we're going to talk about RISC architectures. And the machine that the book chooses to use and we will concentrate mostly on is a fictitious prototypical RISC machine. It's a machine that you can't buy but looks very much like some of the existing RISC machines. It's a subset of probably the one which is closest is the MIPS R2000 machine. And like most of the RISC architecture, it has a simple load store instruction set, which is to say the only instructions that reference memory, unlike everything we've looked at before, are load and store instructions, and all of the ALU operations and so forth reference only registers. It's a machine where the instruction set was designed from the beginning to be easily decoded and pipelined, and was designed to be a good target for compilers. There are many registers which compilers are good at manipulating. There's only one addressing mode, and anything else has to be synthesized in software by the compiler. And there aren't 400 opcodes for the compiler to choose among, as there are for the VAX. In summary, it's a machine that has 32 32-bit registers. They're mostly all equivalent. It's almost silly to draw the picture because the picture is not very interesting. There are simply 32 32-bit registers. There are a couple of registers that have special meaning. In particular, R0 is always equal to 0. If you store into it, you don't affect it. If you read it, it's always 0. And that turns out to be handy for synthesizing some instructions that aren't really present, and we'll see that in a second. There's also another register, R31, which is used in special way for subroutine linkage, but all other registers are, from the hardware point of view, equivalent and can be used for anything. In fact, the software and the compilers and even the assembler make certain standard assumptions about the use of other of these registers, and we may talk about some of those conventions. But as far as the hardware is concerned, they're absolutely equivalent. There's another equal set of 32 32-bit floating point registers when used as single precision. When used as double precision, they're paired in even odd pairs so that you get 16 64-bit double precision registers. It's an entirely separate set of registers from the integer addresses, from the integer registers. Unlike many of the previous machines we've seen, data accesses are aligned. If you're accessing a byte, it can be on any byte boundary. If you're accessing a 16-bit half word, it has to be on a 16-bit boundary. If you're accessing a 4-byte integer or a 4-byte floating point operand, it has to be on a 4-byte boundary. And that's primarily to make instruction execution quick. You don't have to ever fetch two separate words and put together the pieces to access a larger quantity. All instructions are 32 bits wide. And there are only 4 types. And in fact, let's go over the types of those instructions. The first type are the ones that use immediate operations. As in all instructions, opcodes are just 16 bits wide. Register designators take 5 bits because we need to address 32 registers. That leaves over 16 bits for the immediate field. This is the only format used for loads and stores. And the only kind of load and store there is a kind that either loads or stores the destination register and computes the memory address with the only memory address mode, which is add the contents of register RS1 with the 16-bit immediate field. That's used to load bytes, half-words, words, to load signed or unsigned values. If you load a half-word, for example, and you load it signed, then it takes the most significant signed bit and propagates it into the rest of the register. That's the only memory access mode there is. In addition, this mode is used for ALU operations. If you want to add a constant to a register, then you specify that register in RS1. You encode the constant in the 16 bits of immediate, which then gets sign extended to 32 bits wide, and the result is stored in the register specified by RD. I assume this is all fairly straightforward, right? If you wanted to do something like add to register 1 a constant 100, obviously the 100 goes in here. I'm sorry, I need another operand there. R2, 100. The 100 goes in the immediate field, the R2 goes into the RS1 field, and the destination register goes into the RD field. Assembling for a machine like this is fairly trivial. Conditional branches. Conditional branches use this immediate field, and in fact this is a machine on which there are no condition codes. The only thing you can do in this machine is to test to see whether a given register is 0 or not. And if the register is 0 or not, depending on the conditional branch, then you modify the existing program counter by adding to it the signed immediate field. The immediate field is signed and signed extendedly. So you can do a conditional branch to plus or minus 32k bytes, roughly, around the current instruction. This is one of the instructions that differs somewhat in the real MIPS processor, and I think also in the processor that you get to simulate as part of the programming exercises. Is that right? That in fact on the MIPS, conditional tests are not just limited to testing for equality or non-equality. You can in fact compare registers. Notice that there's a register designator that we've chosen not to use, RD, in this instruction. And you could, if you wanted to, design an instruction that compared those two registers and branched depending on whether they were equal or greater than or less than. For reasons why we'll see later, we've chosen not to do that with the DLX instruction set. Jump register is a jump instruction that allows you to entirely specify the new program counter by the contents of a register. In addition, for subroutine linkage, you can decide to save the current program counter, or actually the program counter of the next instruction, in register 31. So if you do a jump and link register to wherever register 3 is pointing, the next instruction, whatever it is, gets its address put into register 31, so that when you want to return from that subroutine, you can just do a jump register instruction that specifies register 31. Simple way to do one level subroutine calling. If you want to do more levels than that, then you have to arrange somehow to save register 31 before destroying it with the next subroutine call. This is also used for a load immediate instruction. And in fact, a load immediate instruction is an instruction which doesn't really exist. Because remember that register 0 is always 0. A load immediate into register 3, say, of some immediate value is actually, or could be, something like an add, where the result is register 3, of the contents of register 0 and the immediate value 100. So in fact, load immediate is a pseudo operation in the assembler. Yeah. All ALU operations. Well, there are ALU operations that have 3 register operands, 2 sources and 1 destination. We'll see that on the next page. One of the things that you can't synthesize with one of these operations is a way to load an immediate value into the upper half of a register, because this immediate value is always sign extended and loaded into the full register, but only the low order 16 bits can be individually specified. In order to allow the upper 16 bits to be loaded, there's a load upper immediate instruction. Yeah. Over here.
So those should be swapped because the destination is the middle one?
No. In fact, as the assembler asks you to write instructions, this is the destination. That, in fact, does not necessarily correspond to the order in which they appear in the instruction. In fact, in this case, it's different. And we'll see, in fact, that the destination register is not even always in this field. It moves to a different field in a different instruction format. But as far as the assembler is concerned, you always write the destination as the first operand. That's an arbitrary convention. Okay, these were the instructions you were just asking about, in fact. These are the traditional 3-operand ALU operations. You specify 2 source operands and 1 destination operand, and all of them are register numbers. Notice, in fact, that the destination register in this case moved from where it was in the previous format to someplace else. It couldn't have been here in the previous format because we needed all of these 16 bits for the immediate field. And it can't be here for a reason which we'll see in about a week, having to do with the way the pipeline instruction set works. So these take a function specified as a combination of opcode and these 11 bits and perform that function on the two registers and produce the result in the destination register. The normal complement of adds, arithmetic operations, shifts, compares. Remember that branches only compare to see if the register is 0 or not. In order to do more complicated compares, we've got to generate something that we can test against 0. So a compare instruction might say, if register 5 is less than register 6, then set register 1 to 1, otherwise set it to 0. And then we can use that register 1 later in a conditional branch instruction. Now why is this function here? Well, the reason is that 6 bits didn't give us enough opcodes to be able to encode all of the different register-register operations there are. So in fact, for most of these, what the opcode simply says is ALU type operation. And the details of which ALU type operation it is encoded somewhere in these other 11 bits. In fact, even in the MIPS 2000, the number of bits that shifts do is encoded in here. In fact, this is divided up into 2 fields, one of which is really the function, and the other is another 5-bit field that specifies the number of positions to shift. So these R-type instructions do essentially all of the arithmetic, including floating point arithmetic. Questions about that? Notice that what is not there are any of the complicated data types. There's no string operations, no decimal operations, no character operations, just integer and floating point operations. The final instruction type is used for jumps. And in a simple jump, at least in DLX, the jump simply adds what is now a 26-bit offset to the current value of the PC and lets you get a wider range. This is not a conditional jump, this is an unconditional jump. If you need to do a conditional jump to a place which is more than 32k bytes from the current instruction, you've got to do a branch conditional around a jump instruction that takes the long leap elsewhere. And like for the jump register, in addition to the simple jump format, there's also a jump and link format used for subroutine calls where the address of the next instruction is saved in register 31. This is also somewhat different from the real MIPS processor. The real MIPS processor actually has jump instructions that are not simple additions to the PC. They involve a combination of some high-order bits of the PC with the value specified in the offset, and in fact, in that case, the offset is a word offset rather than a byte offset. But this turns out to be a much simpler kind of jump instruction to describe and to implement in the machines that we'll see. Any questions about DLX? We'll get to see it in more detail and see variations of it that are implemented in the programming assignment. And if you're interested, you can also look at variations of it for other RISC processors. Now notice a couple of things that we'll talk about much more later. Let me just hint at what's coming. That because of the pipeline implementations, some of what seem to be simple instructions are not really as simple as they seem. Because it's hard to do branches quickly, it's very convenient to define the branch so that the instruction following the branch gets done anyway. And in DLX and in MIPS, the one instruction which follows a conditional branch is executed whether or not the branch is taken. So if you do a conditional branch instruction and go somewhere, the following instruction might be an add instruction. That add instruction is executed even if you take the branch. Sometimes it's hard to find an instruction to put in there, which is convenient. Sometimes you can take this add instruction, or the instruction which used to be before the branch, and move it to after the branch, as long as the branch doesn't depend on it. That's always a safe thing to do. But sometimes, in fact, you've got to waste this instruction by putting a no-op in there because you can't find an instruction that makes sense to do whether or not the branch is taken. And we'll discuss these kinds of things in much greater detail later. Loads also present a problem because loads go to memory, and memory takes such a long time. It's convenient to the implementer of the instruction set not to allow the result of a load instruction from memory to be used in the subsequent instruction. And in fact, in the MIPS architecture, as specified at least, the instruction following a memory load may not use the destination register of that load. And if you do use it, you'll get undefined results. You might get the previous contents of that register. You might, depending on the implementation, get the new contents of that register. It's basically something you're not allowed to do.
Why didn't they have just the processor stall if that was the case?
You could do that. And in fact, most implementations of even MIPS processors do that. But in fact, MIPS does not stand for millions of instructions per second. MIPS stands for microprocessor without interlocked pipeline stages. And what that really means is they didn't want to stall. They didn't want to design anything into the implementation that required them to stall. And in order to allow that, they had to require that the following instruction not use the destination of the load. In fact, they've given that up. And in all reasonable and certainly all recent implementations of processors like this, there are interlocks. And if you, in fact, do use the destination of that store instruction, the processor will simply hiccup, stall for a while, wait until it's available, and then use it. They were trying to be purists, I guess, is the short answer. We'll talk about this kind of elaboration of branches to make the delay slot following the branch more useful later on. That basically is the sort of purist approach to RISC machines. And the MIPS, or at least the early MIPS, were probably the most pure of those machines. But most of the commercial implementations of RISC processors, in fact, all succumb to the temptation to elaborate the instruction set in one way or another. And what I want to do, in the interest of giving you a picture of real life, is to describe briefly what some of those other RISC variations are and which machines actually use them. Here's one which I think only the Spark uses, and it's a concept which is actually a clever idea dating back probably at least 10 years, which is to have register windows. As in the DLX instruction set that we just saw, there are at any given time 32-bit registers always visible. But in fact, the processor has a lot more registers like that, and only some of them are visible at a time. And the time at which other registers are visible are the time when you do a procedure call. So this represents the 32 registers accessible at any given time to a program. When you make a subroutine call, you get a different set of registers. But they're not a brand new set of 32-bit registers. In fact, they share 8 registers in common. The software convention is that the 8 registers they share in common with the previous subroutine are the parameters that are getting sent to the new subroutine. So outs refer to the parameters that this subroutine wants to send as inputs to the next subroutine. So you get 16 new registers, and you get 8 old registers from the previous procedure. What does that mean? Well, it means you don't have to save any registers because the ones you're about to use are brand new registers. The previous procedure's input registers and local registers are hidden from you. They're in the processor somewhere, but you don't see them. You don't have to save them. And so on. So each call, this transition, is a subroutine call instruction. Each transition gives you 8 of the same registers as the previous subroutine, 16 new registers, of which you can use 8 for your temporary variables, and 8 as output registers for the next subroutine you're going to call. This adds up to 24 registers, and in addition, they have 8 of the registers which are always global, always the same, regardless of which subroutine you have to be executing in. Now notice that the number of physical registers that the processor may have is unspecified by the architecture. You can have as many as you like for as many as you like, as deeply as you like subroutines to be called. Well, there are a couple of problems with this. One is, what happens when the wily programmer nests his subroutines one level more deeply than the processor happens to have registers on chip? You can't disallow that. You can't not allow him to call subroutines as deeply as he likes. So there has to be a mechanism, in fact, to eventually dump these old sets of registers out into main memory to free up hardware registers to be used for the next subroutine call. And similarly, when you do subroutine returns, you've got to be able to fetch back those saved registers from memory. That adds considerable complication. Another complication is that you now have, instead of 32-bit registers, instead of 32 registers as part of the context for the task that's currently running, you have 56 or 128 or 256 or as many as you want to provide in the implementation. And every time you switch from one task to another, you've got to dump all of those registers out to memory and reload all of those registers from the other task. So it makes context switching somewhat slower. Question?
What if you have more than 8 ins and outs?
If you have more than 8 ins and outs, you're stuck. You've got to do something else. And that something else is typically pushing it on a stack in main memory. But that's no different than even in a simple DLX architecture where you're using registers to pass parameters. You typically use a few of them to pass parameters, and if you have more than that, then you've got to store them in memory somewhere.
All these trade-offs on the little running around to speed up? I mean, I guess not too many other places have done this before.
I'm sure you would get different answers to that question depending on who you ask. I don't know of any scientific study that I would believe that enables you to determine whether this was a good thing to do or not. Obviously, the people at Sun who follow the Spark architecture believe that this was a good thing to have done. It's a complicated evaluation because it depends a lot on how clever your compiler is and what kind of programs you measure and so forth. I don't think there's a scientific answer to the question about whether this is good or not. Okay, that's what Spark has that's cute. Here's what PowerPC has that's cute. Remember that one of the things we talked about is that a global condition code makes it hard to build high-performance implementation because it's hard to pipeline. It's hard to insert instructions in between an instruction that sets a condition code and one that uses it because you may likely destroy the condition code. What we did for DLX and what many of the RISC machines do is to have an explicit, is to have no condition code, and in fact the branch instruction tests registers instead. Well, the PowerPC has a compromise. They have a condition code register, but in fact it has not just one, but 8 separate and independent condition codes. And when you write instructions, you get to specify which of those condition codes get set. There is one of those 8 sets that in fact is implicitly set by integer operations if you request it. There are 2 forms of the add instruction. There's an add that doesn't set any condition codes, and then there's another one, and it's written in assembly language by saying add dot, that does set one of those 8 condition codes. The dot basically turns on an extra bit somewhere in the encoding of the instruction that says you're supposed to set the condition code. So there's one set that gets set implicitly by integer operations if it wants it. There's another set that gets set by floating point operations if that instruction wants it. And then there are 6 other condition codes that are available to be set by compare instructions. So you could write an instruction that says compare register 3 to register 4 and set condition code 6. And other compare instructions could be setting other condition codes, and they're independent of each other. The branch instructions then can test any of those 8 sets of condition codes. So you can interleave the setting of condition codes with the testing of condition codes and be able to get a higher performance implementation. Halfway between what the MIPS-like machine does and what the VAX-like or 8086-like machine does. I think we've talked about all of that. Okay, let's look at another variation, the DEC alpha. One of the things we'll see, and you probably already know, is that branches are very hard to make go fast. One way to make them go fast is to make them disappear. And you can make them disappear when, if you're writing a simple if expression that, let's say, assigns a variable, rather than compiling that into a test that branches around the assignment of that variable, define an instruction that's a conditional register move instruction that says if a register has a particular relationship to 0, then you do this assignment, otherwise you don't. Obviously, the people who designed the DEC alpha instruction set thought that this was common enough that it was worthwhile doing. And measurements, depending on who make them, may or may not support that conclusion. Unlike many of the other RISC machines, the DEC alpha has scaled array indexing, like the 8086. It has byte manipulation instructions that allow you to compare, extract, insert, mask, and zero out individual bytes rather than larger objects. Let's skip this one for the moment. It also has what amounts to a reinvention of an old implementation technique called microprogramming. Since many of the operations that you would like to include in the instruction set are things that don't make sense to do in a RISC-like architecture, they basically have an escape that allows you to take the kernel RISC instruction set and execute or emulate more complex operations. So these, they call this the privileged architecture library. Basically, it's RISC-like instructions executing out of main memory that have access to special internal machine state. That allow you to do things like complex interrupt dispatching, complex virtual memory control, that in a CISC architecture would be part of the standard instruction set. And in the DEC alpha are part of a no man's land. It's not part of the base instruction set yet. It's not part, simply something that's implemented using the base architecture, the base instruction set. It's basically microcode that runs out of main memory that has special access to internal registers. Another feature of the DEC alpha, incidentally, is that for compatibility, they support both the IEEE floating point format and the VAX floating point format. Much as the 8086 architecture was influenced by having to be compatible with older machines, the DEC alpha was as well, and has to institutionalize and support as part of its instruction set both floating point formats. Just briefly, what it is about the HPPA RISC that looks strange. One thing which is remarkable is that even though it was one of the earlier machines in the mid-80s, it had a 64-bit address space, which the recent RISCs are only now getting around to having. It also has a variety of complex addressing modes, including some which are the bane of pipelined implementations that allow registers to be auto-incremented in some fashion during execution. It, unlike most of the other RISCs, supports packed decimal data. And we're running out of time, so I won't go through the rest of this, but also supports other complications. I guess the point of going through some of these examples is to show you that although RISCs tend to be more like each other than CISCs, there still is a wide variation. The tendency over time is for RISCs to become more CISC-like as people add these complicated modes. On the other hand, the tendency is for CISCs to become more RISC-like. So the pendulum is swinging a bit in the last several years, and in fact, RISCs and CISCs are beginning to converge. See you next time.